Now we'll move on to a one-tailed t-test to see why this is different. Note as well here in the problem, we're looking at a situation where we are considering a manufacturer's claim that the capacity of the batteries is at least 140 hours. And of course, if we're using them for our iPod, we want to know that it's going to last at least as long as the manufacturer suggests. We don't mind if it's longer, but we'd be concerned if it was smaller than that value. So this makes it a one-tailed test. Now again, writing that statement, the mean is at least 140, means that we can write an alternative statement, the complement of that one, that says the mean is less than 140. And here again, going back to our idea of writing down the null and alternate hypothesis, we select the one that contains the inequality symbol without the mean value there. And that means we can state our alternate hypothesis. Mean is less than 140, which immediately then defines for us our null hypothesis where the mean is equal to 140. So we're doing our single test at the mean equals 140 to determine if we can support that claim or not. Notice here as well the underlying statement of an assumption of a normal distribution. And we need this for a t-test. We need to know that we're given sample statistics. Here we have the mean and standard deviation, and we are assuming a normal underlying population. Furthermore, note here the value of alpha is being given, the alpha value of 0.05, which we will have all at one end of the distribution here for our t-test. So let's go on to look at the example and how we'll fill in the information on our template. So again here, we're looking at a one-tailed test. We have the null hypothesis is that the mean is equal to 140 against the alternate hypothesis that the mean is less than 140. And using the values of alpha, which were stated as 0.05, and remember degrees of freedom for a t-test, sample size -1, so 20 minus 1, that's 19 degrees of freedom. Our critical value this time, we put all of the alpha at one end, so it's at the left-hand end because we are rejecting if the mean is less than that value. So our critical value here has the entire alpha value, all of alpha, 0.05, at the bottom end. So our alpha value all at one end, not this time divided by 2. So to find that critical value, again I'm going to go back to the critical t table. Of course you can use Excel for this, but for our purposes today it's more straightforward to use the t table. We have 19 degrees of freedom this time. So I'll put the paper across at 19 degrees of freedom. We can see the numbers at the bottom of the screen there. And this time our alpha value, all at one end, the area in one tail, is 0.05, and this means that we're looking at the number here, 1.729. So I'm writing 1.729 in the critical position, but of course, it's not 1.729 because it's on the left-hand end. So the tables and Excel will give us a positive value, but we know that this is a symmetrical distribution with 0 in the middle, which means that we need to make that negative, minus 1.729. Again, our test statistic, now we have the critical value. We can say we can reject the null hypothesis. Again, some people like to see this in words. If our calculated test statistic is less than negative 1.729, that's our rejection criterion this time. The test statistic, using that same formula again, x bar, sample mean, minus the population mean, divided by sample standard deviation over the square root of n. our test statistic this time, the sample mean in the problem was 138.47. You can go back to the previous slide to check that. It's not magic. It comes from the sample statistics. Our population mean is 140, and we're dividing by the sample standard deviation S, which was given as 2.66. In real life, we'd calculate that value, and we're dividing by the square root of sample size, which in this case is 20. Again, when you're calculating this for yourself, do it in steps so you know that the numbers seem reasonable. The denominator value there, the value on the bottom line, 2.66 divided by the square root of 20, I have 0.595 there. And the number on the top line, 138.47, take away 140, I've got minus 1.53. And these are two decimal place values, giving me a test statistic of minus 2.57. So minus 2.57, where does that lie in our distribution? Of course, it's going to be over here on the left-hand end. It's even bigger and negative. So minus 2.57 is clearly in the rejection region. Our decision would be reject H naught, since that value is smaller than the critical value. So reject the null hypothesis. Our evidence is that minus 2.57 is less than minus 1.729. And this time, the conclusion is that we have evidence that the claim is incorrect. This time we have evidence to suggest that the mean value is less than 140. Notice that we have evidence to accept the alternate hypothesis if we reject the null hypothesis. So again, in the context of the question, we have evidence to suggest the mean is less than 140 ampere hours, which means that the claim is incorrect.